So we got section 6.1. It's entitled Inner Product, Length, and Orthogonality. And so we're going to deal with the inner product first. Okay, so let me define the inner product. It's also called the dot product. That's another word for it. And so we're going to define the inner product U dot V as U transpose V. And so this is how we're going to define our inner product or dot product. Okay. Quick example. Let's let U be the vector 2, -5, -1. And we'll let V be 3, 2, -3. Let's find U dot V. So we're going to find the dot product of your V. Okay, so by definition, this is U transpose V, which is 2, -5, -1 times 3, 2, -3. Okay, and so we just multiply these two matrices. We have 3 times 2, or 2 times 3, plus -5 times 2. And then finally, we'll have -1 times -3. And if we simplify, this is 6 plus -10 plus 3, which is -1. And there we go. So U dot V is -1. Okay. If I had to compute V dot U, this would be V transpose U. Okay. Which should give us 3, 2, -3 times 2, -5, -1. If we do that, we also get 3 times 2, 2 times -5, and -3 times -1, which would be the same, -1. And so this is the inner product or the dot product. And so we have the following properties that are true. So this is going to be our first theorem in chapter 6. We're going to call this theorem 1. And it says let U, V, and W be vectors in Rn. And then we're going to let C be the scalar, be a scalar. Then we have the following properties. The first property says U dot V is equal to V dot U. Okay. Second property, U plus V dot W is equal to U dot W plus V dot W. So we have the Streeter property. Likewise, Cu dot V is equal to Cu dot V, which is equal to U dot CV. And finally, the fourth property says U dot U is greater than or equal to 0. And U dot U is equal to 0 if and only if u is 0, or the 0 vector, if u is the 0 vector. Okay, so this is my first theorem. So my next definition is going to be the length, or also called the norm. So the length, also called the norm, of v is the non-negative scalar all right, so it's v with two vertical bars beside it, so I would define a norm. So my definition, my norm of v, or my length of v, is equal to the square root of v dot v. All right, so it's equal to the square root of v dot v. We can also say, if we square both sides, the length squared is equal to v dot v. Okay, so let's do an example. Oh, well, before we jump to the an example, a vector whose length is 1 is called a unit vector. It's called a unit vector. And so if we divide a non-zero vector v by its length, uh, so we say a non-zero vector divided by the norm of v, that's the length, we can obtain a unit vector. Uh, okay, and so the process of creating a unit vector is sometimes called normalizing v. Okay, I'm going to show you how to do that shortly. So let's do a quick example. We're going to let v be 1, -2, 2, 0, and we want to find a unit vector, u, in the same direction as v. All right, so v is going to be that vector. So we want to find a unit vector, and we're going to call it u, that's in the same direction of v. So the first thing you want to do is you want to find the length. So first, let's find the length. All right, so that's the first thing I want to do, find the length. Okay, and so we know that the length uh, squared is equal to v dot v. And so that's what we're going to do first. We're going to find the length of v dot v. Well, the length of v dot v is just going to be 1 squared -2 squared. So v dot v, by definition, is v transpose v. And so if I set that up as a matrices, I have 1, -2, 2, 0 times 1, -2, 2, 0, which is just, so v dot v is just those entries, 1 squared plus -2 squared plus 2 squared plus 0 squared. All right, so that's a little shortcut if you ever want to figure out v dot v or u dot u. It's just going to be those entries squared. And so this is equivalent to 1 plus 4 plus 4, which is 9. All right. And so my length, so this is just so this is my norm squared. So my norm is equal to the square root of v dot v, right? And so this is the square root of 9, which is 3. So my length, or my norm in this case, is 3. So then what we're going to do is we want to multiply v. So we want to multiply v by 1 over the norm of v. All right. And if we do that, we have, we're going to call that u. U is going to be equal to 1 on the norm of v times v, which is 1 over 3 times v. And so we get 1/3 of our matrix, or our vector 1, -2, 2, 0, which is 1/3, -2/3, 2/3, and 0. Okay. And so our unit vector u is going to be this vector here: 1/3, -2/3, 2/3, 0. Okay. We can also, if we wanted to, we can check to make sure the norm of u, or the length of u, is 1. So that's how we're going to check to make sure this is a unit vector. So in other words, we can just show that the normal u squared is equivalent to 1. And so you can check it working that way. So let's just check our work really quickly, just to show you that it is a unit vector. So let's check our work. Let's check to make sure that the norm of u squared is equal to 1. So that proves that u is a unit vector. All right, so the length of u squared is equal to u dot u. So like I said, this just be my elements of u squared, which is 1/3 squared, -2/3 squared, 2/3 squared, plus 0 squared. Okay, this is equal to 1 over 9 plus 4 over 9 plus 4 over 9, all right, which is 9 over 9, which is 1. And so there we go. U is a unit vector. Okay, so that's how we're going to find a unit vector. So basically what we need to do, we need to figure out what's our length. After we find our length, we want to multiply our length by 1 over the length. Multiply our vector v by 1 over that length to find our unit vector. Okay, let's do this next example. It says let W be the subspace of R2 spanned by X. And so that's going to be the vector 2/3, 1. We want to find a unit vector Z. So we want to find a unit vector that spans what is a basis for W. All right. So we want to find a unit vector Z that's going to be the basis for W. All right. All right. So W is going to consist of all the multiples of X. All right. So any non-zero vector in W is going to be a basis for W. All right. And so to simplify, we need to what we need to do, we kind of need to scale x to eliminate these fractions. So let's multiply x by 3 so that we're going to scale it so we can get rid of that fraction. So we're going to multiply x by 3 to get rid of the fraction. We're going to call it y. All right. So first, we're going to scale x by 3 to form y. And so we're going to call y is going to be the vector 2, 3. We just multiply x times 3. All right, so basically I said y is equal to 3x. Okay. Okay, so we're going to let y be 2, 3. Okay, so now what we need to do, we need to compute the norm or compute the length. Okay, so let's find y, the length of y squared. Okay, and so this is going to be 2 squared plus 3 squared, which is 13. All right, and so that means my length must be the square root of 13. All right, by definition. And so let's normalize y. So now normalize y. All right. So to normalize y, we're going to say, we're just going to say y, 1 over y, 1 over the length of y times y, right? So we're going to call z. It's going to be 1 over y times the length, 1 over the length of y. So 1 over the square root of 13 times y. Okay, and so we get the new vector 2 over square root of 13, 3 over square root of 13. And so there we go. So we just found z that is the basis for w. So basically we just had to normalize it. First we scaled x to make it easier to work with. Then we found a norm, and then we normalized it. All right. So let's move on to distance. For vectors u and v and Rn, the distance between u and v and we write it as distance or dist of u and v is the length of the vector u minus v. So it's going to be u minus v. And so we can write it as the distance of uv is going to be the length or the norm of u minus v. Okay, so this is how we're going to find the distance. All right, so we're going to let u is going to be the vector 7, 1, and v is going to be the vector 3, 2. Let's find the distance between u and v. So u minus v is equal to, so this is 7, 1 minus the vector 3, 2, which will give me 4, -1. Okay, so let's find the length of u minus v, which will be 4 squared. So let's find the length squared, which is 4 squared plus -1 squared. So that's 16 plus 1, which is 17. So that means my length of u minus v is the square root of 17. So now let's move on to orthogonal vectors. So orthogonality is basically another word for saying perpendicular, but using vectors. All right. So the rest of the chapter is going to depend on the fact or the concept of perpendicular lines in this in Euclidean geometry. And so basically, what we're going to do is we're going to determine if vectors are perpendicular. All right. And so that's what it means to be orthogonal. Okay. So two vectors, u and v, and Rn are orthogonal or perpendicular if u dot v is equal to 0. So that's going to be my definition for orthogonal vectors. So basically, the two vectors, u and v, and Rn are orthogonal if u dot v, the inner product, is equal to 0. Okay. And of course, it's clear to note that the 0 vector is pretty much orthogonal with any or every vector, every other vector in the Rn. All right, so if I have the 0 vector, of course, it's going to make 0 with any vector. Okay. All right, so that leads us to our next theorem, which is the Pythagorean theorem. All right, so two vectors, u and v, are orthogonal if and only if the length of u plus v squared is equal u squared, which is the length of u squared, plus the length of v squared. All right, so we have a Pythagorean theorem for vectors with orthogonality. Okay. So also I want to point out before we go the complement. All right, so let's just say if z is an orthogonal vector, if z is orthogonal to every vector in a subspace W of Rn, then it's clear to say z is also z is said to be orthogonal to W. Okay, and the set of all vectors z that are orthogonal to W is going to be called the complement, the orthogonal complement. It's the orthogonal complement of W. And we write that complement as W with a backwards T for my superscript. And so we can read this. We instead of saying W, the complement of W, we read that as W perpendicular or W perp. So we read it as the perpendicular, W perpendicular. Okay. All right, moving to session two. Session two is going to be orthogonal sets. Okay. And so a set of vectors U1 to UN or UP and Rn is said to be orthogonal set if each pair of distinct vectors from the set is orthogonal. Uh, Basically, what that means is if uj dot uj is equal to 0 whenever I is not equal to j. So it's ui dot uj. So whenever I is not equal to j. So there we go. So let me show you a quick example. So we need to show that uj, well, we're going to show that this set of vectors u1 to u3 show that this set is orthogonal. All right. And so we're going to let u1 is going to be the vector 3, 1, 1. u2 is going to be the vector negative 1, 2, 1. And we're going to say u3 is the vector negative 1 half, negative 2, 7 halves. All right. And so, in other words, I need to consider all pairs, all possible pairs. There are three vectors in this set. And so, since there are three vectors there, I can do u1 and u2 together. So I can do u1 dot u2. I can do u1 and u3 together. And now I can do u2 and u3 together. So those are all of my possibilities. So each pair, I need to consider all possible pairs and make sure each one is orthogonal. So make sure the dot product of each pair is equal to 0. That's how we show that the entire set is orthogonal if each pair in the set is orthogonal. So let's do u1 dot u2. So if I do u1 dot u2, this is going to give me 3 times negative 1, 1 times 2 plus 1 times 2, and then 1 times 1. Okay, let's see if that gives me 0. This is negative 3 plus 2 plus 1. That's correct. That's 0. Okay. U1 dot U3. So 1 and 3 goes together. So this will be 3 times negative 1 half, 1 times negative 2, and finally 1 times 7 halves. Okay, so that's negative 3 halves minus 2 plus 7 halves. So negative 3 halves and 7 halves makes 4 halves, which is 2. So 2 plus negative 2 is 0. So that's 0. And so finally, let's check u dot 2, u2 dot u3. And this will be negative 1 times negative 1 half plus 2 times negative 2, and then 1 times 7 halves. And if we check that out, we should also get 0. All right, since each pair and this so each pair of since each pair of vectors in the set is orthogonal, their dot product is 0, then we can conclude that this is an orthogonal set. So u1, u2, u3 is an orthogonal set. Okay. So that leads us to a theorem, call it theorem 4. It says if S is a set of u1 to use a P, is an orthogonal set of non-zero, so it's going to be non-zero vectors in Rn, then S is linear dependent. Linear independent. And since it's linear independent, we can say it's a basis for the subspace spanned by S. So there's a proof in the book, so I won't prove it. I'll let you see the proof in the book. Uh, let's move to the next definition. Orthogonal basis. So an orthogonal basis for a subspace W, all right, it's a basis. It's a basis for W that is also an orthogonal set. Theorem 5 says we're going to let the set U1 to use a P be a basis, be an orthogonal basis. For subspace W of Rn. For each Y and W, the weights in the linear combination Y is equal to C1 U1 to CP UP. The weights are given by C sub j is equal to y dot u sub j over u sub j dot u sub j. So j is equal to 1p. Okay, just do an example. All right, we're going to let the set S be u1, u2, u3. We're going to use the same one we used from the first example. All right. All right. And so we know that's an orthogonal set, and that's the basis for R3. It's going to be an orthogonal basis for R3 by our theorem. All right, so what we need to do, let's express the vector y, which is going to be 6, 1, negative 8. We want to express that as a linear combination of the vectors in S. So we want to express y as a linear combination of the vectors in S. Okay? So a few things that we need to compute. We need to compute the dot product of y and u1, which is going to be, so recall our vectors from example 1. I need to write them somewhere. So we'll let, we say u1 was 3, 1, 1. u2 was negative 1, 2, 1. And u3 was negative 1 half, negative 2, 7 halves. All right, so we need to figure out a few things. So we need to figure out y dot u1, y dot u2, y dot u3. All right, we also need to figure out u1 dot u1, u2 dot u2, and u3 dot u3. Okay, so I just want to follow theorem 5. All right, so I need these components. Okay, so y dot u1 is going to be y transpose u1 would be 6 times 3, and 1 times 1, and 1 times negative 8. So that's 6, 1 minus negative 8. And so we get 11. So yeah, 3 times 6 is 18. Yeah, we get 11. 6 times 3 is 18. 1 times 1 is, or 1 is going to be 19 minus 8, which is 11. So y transpose u2, that's y dot u2, is going to be 6 times negative 1, 1 times 2, and negative 8 times 1. And so we should get negative 12 for this one. Y dot u3 is going to be negative 33. U1 dot u1 is going to be 3 squared, 1 squared, and 1 is 9, 10, 11, which is also 11. U2 dot u2 is going to be 1, 4, and 1, which is 6. And u3 dot u3 is going to be negative 1 half squared plus negative 4 squared plus 7 half squared. It's going to be 33 halves. Okay. And so by theorem 5, we have that y is equal to, all right, and so I need C1U1, which is given by y dot u1 over u1 dot u1. That's how I find my c1. So this is going to be c1 then times u1 plus y dot u2 over u2 dot u2 times u2 plus y dot u3 over u3 dot u3 times u3. Okay, and so this is equal to, so basically this is my y is equal to c1u1 plus c2u2 plus c3u3. And so remember we found c sub j by saying that's equal to y dot u sub j over uj dot uj. And that's what I'm finding now. And so let's plug in our substitution. So y is equal to 11. So y dot u1 is 11. u1 dot u1 is 11 as well. So 11 over 11 times u1 plus y dot u2, which is negative 12 over 6. All right, negative 12 over 6. Then times u2 plus negative 33 over 33 halves. All right, times u3. And so we get u1 minus 2u2 minus 2u3. So we just wrote y as a linear combination. Okay, so there we go. So lastly, let's talk about an orthogonal projection. And so we're going to call this y tilde. All right, and so I'm just going to go ahead and give you the definition for it. So y tilde is going to be y dot u over u dot u times the vector u. Okay, so we're going to, a quick example on how to use this formula. We're going to let y be the vector 7, 6, and u is going to be 4, 2. Find the orthogonal projection of y onto u. Then we want to write, then let's write y as the sum of two orthogonal vectors. Okay. All right, so we want one of them to be, I want one of them to be in the span of u, and one is to be orthogonal to u. Okay. All right, so I need to compute y dot u and u dot u. So y dot u is going to be 7 times 4 is 28. 6 times 2 is 12. So 28 and 12 makes 40. Okay. And I also need to compute u dot u. U dot u is going to be 4 squared plus 2 squared, all right, which is 16 plus 4 is 20. Okay, and so my orthogonal projection, y tilde, orthogonal projection from y to u is going to be y dot u over u dot u times u, which is going to be 40 over 20 times u, which is going to be 2 times u. U is 42, which is 84. All right. So orthogonal projection is going to be the vector 8, 4. All right. And so the component of y orthogonal to u, so the component of y orthogonal to u is going to be y minus y tilde, which is y is 7, 6 minus 8, 4, which is negative 1, 2. Okay. So that's my component of y orthogonal to u. All right, the sum of these two vectors, the sum is going to be 8, 4 plus negative 1, 2. All right, so I'm gonna add in my component of y orthogonal to u. I'm adding that with my orthogonal projection. That's going to give me 7, 6. Okay, so that's y, uh, y tilde plus y minus y tilde. We're gonna call that y. So that means, so this shows that the set y tilde and y minus y tilde is an orthogonal set. Okay, and so we can check this by to make sure it's equal to 0. If I do so I can check by saying y tilde dot y minus y tilde. That's 8, 4 dot negative 1, 2. I need to check to make sure that's 0. All right, so the transpose will be 8, 4 times negative 1, 2. So that's negative 8. 8 times 1 is negative 8 plus 4 times 2. And of course, I get 0. So it's true that this is the orthogonal set. Okay. So we wrote y as the sum of two orthogonal vectors. And I showed that the span of u.